Section 1.3 is called Right Triangle Trigonometry. And it starts with kind of a 1.2 flashback. I just want to kind of remind you or think about Section 1.2 one more time real quick. It says, recall that we can find the sine, cosine, or tangent, or whatever, cotangent, secant, cosecant. We can find the sine, cosine, tangent, etc. of any angle as long as we know the what of where the angle's terminal side intersects the unit circle. What would, as far as what we did in 1.2, what do we need to know about the angle with it when it comes to the unit circle, so we can find sine, cosine, or tangent? Well, if we knew the coordinates, right? Because again, think back, we would figure out the sine or cosine or tangent, etc., using those definitions that involved x, y, and r. And if it was the unit circle that these coordinates lied on, the radius would have been what? The unit circle has a radius of 1. So we would find the sine, cosine, tangent by plugging in for, the sine would be y over r, so we would need like a y coordinate over r, and so on. So as long as we knew the coordinates, and really quick, and there should be an S here. I think my flip chart or whatever on my projector screen went a little bit out of bounds here, so that should say coordinates plural, as long as we know the coordinates. That makes me mad that happened. Anyway, let's see. So moving on, where were we? This is what I just kind of talked about a second ago. Because we know the definitions in terms of the unit circle. That'd be the x over r, y over r. That's a little bit out of order, but y over x, etc. We know those definitions. This includes, the really, really nice coordinates of 1, 0, which would be for 0 degrees, 0, 1, that would correspond with, those would be the unit circle coordinates for 90 degrees. -1, 0 would be the unit circle coordinates, of course, for 180 degrees, and so on. Okay, so these would be the really, really nice coordinates on the unit circle. Okay, and I'll point this out. It's kind of I can't help but point out that in this little picture we have here of the unit circle, looks like I've drawn a right triangle. So section 1.3, as we now start to get into 1.3 here now, the new stuff, it's going to be about right triangles. So if the coordinates of this point are x, y, whatever, whatever, then what would be behind this box? Like how long, or what is the length of this side of the triangle? Well, wouldn't it just be whatever the y coordinate is? And what is the length of this side of this red triangle? Well, wouldn't it be whatever x is? Whoa, that's a lot of boxing. So now for 1.3. Notice the right triangle that we drew in the unit circle. At least for now, let's concern ourselves less with the unit circle and more with right triangles when working with trig functions. In fact, let's tweak our definitions accordingly. So let's tweak those y over r, x over r, y over x, and so on. Let's tweak those definitions and make them sort of fit and correspond with this right triangle stuff. Maybe you can think back to geometry or junior high. What do we label the sides of a right triangle? Particularly a right triangle. What do we call the hypotenuse? Oh, kind of goofed there. Oh well, whatever. Anyway, so there we go. I sort of, spoiler on accident. What I meant to say was, what do we call the longest side of a right triangle, which goes across from the 90 degrees? We call that the hypotenuse. So which one's the hypotenuse here? What would be for sure the longest side? That one, because we know it's across from the 90-degree angle, and so that would be the hypotenuse of that triangle. But what do we call the other sides? Do you remember from like junior high-ish? We call them legs, but we're going to have to kind of differentiate between the two legs, right? So if that's theta, and what the bottom line here is, we need kind of like an angle of reference, a point of reference to differentiate between the two legs. And so according to this angle, like if we were referencing from this angle, then this leg would be the opposite leg, and the other leg would be the adjacent leg. All right? So if that is our theta that we're referencing or having like kind of a point of view from, this is opposite, that's adjacent. To elaborate a little bit, if we were looking at this angle as our theta or our point of reference, then this leg would have been our opposite leg, and this leg would have been our adjacent leg. So whatever leg is opposite and whatever leg is adjacent totally matters where theta is, or whatever angle or corner of the triangle you're talking about. I mean, notice that this leg, this side, was opposite or like across on the other side. And the word adjacent in the English language, it's a fancy vocabulary word for just next to. You know, maybe your English teacher back in the day talked about how, your neighbor, the family or whoever lives next to you, the house next to you, they live adjacent to you. So again, adjacent is just a really fancy word for next to. So can you kind of notice how it fits here? The adjacent leg is right next to theta, okay? While this is like opposite of. Anyway, so if this is, moving on, finally, if that is our theta point of reference, then which leg would be considered opposite of that? This one. And of course, this leg would be considered adjacent. This third triangle, which of these two legs would be considered adjacent to theta? This guy. And that would be opposite. All right. Now, what we're going to kind of write down next is our new versions of the definitions. How do we define the sine of theta? We've already defined it as y over r, if that's what we're working with. If we're working with coordinates and x values, y values, a radius of 1 on a unit circle, whatever. That's how we define sine. But how do we define it using lingo like this? Well, this might not even be new to you. If you got this far in geometry, per se, with Mrs. Clute or Miss Fetchko or whoever, maybe you remember that we would now define sine, cosine, and tangent like so. We would define sine as opposite over hypotenuse. Now I want you to notice that sine of theta, and what would make this picture complete is putting a theta right there. Okay? In fact, maybe that would be good. Anyway. So, if that's theta, then the sine would be y over r, where r would be right here. And maybe we should sort of label that as r. Makes sense? But, so if sine is y over r, if we thought of this more as like, opposite and adjacent and hypotenuse, wouldn't this y value basically be the opposite leg? And wouldn't r be the hypotenuse? So these definitions are not brand new. They're just kind of saying the definitions from 1.2 just in another way. So again, sine is the opposite leg over the hypotenuse. Cosine would now be sort of translated to adjacent over hypotenuse, and the tangent would be translated, and it would basically be the opposite leg over the adjacent leg. And the classic memory trick, the acronym, I believe it would be called, hope I'm not wrong about that, is SOHCAHTOA, and a lot of people help to even stick this more in your brain. SOHCAHTOA, you'd probably be able to see that as being like the name of an Indian chief, the great Indian chief SOHCAHTOA, and whatever. But it is the classic way to remember these definitions, and this is probably not even the first time you've heard SOHCAHTOA. But it goes SOH because of sine being equal to opposite over hypotenuse, and then CAH for ca, which is, of course, that would be the cosine is the adjacent over the hypotenuse, and TOA is tangent equals opposite over adjacent. So remembering how to spell out SOHCAHTOA would help you remember these definitions. All right, so this example problem, which you might see on homework or a test or a quiz or whatnot, says, find the value of each of the 6 trig functions of theta in the figure. So they give you this figure, and it's a triangle, okay? And so in order to find sine, we, of course, are going to plug in the opposite leg and plug in the hypotenuse, right? So the opposite leg is going to be 3, but what's the hypotenuse? We don't know the hypotenuse. Can we figure out the hypotenuse? I mean, can we do a little bit of extra work, go the extra mile, and figure out the hypotenuse as like a side step and side work? Well, if you remember something called the Pythagorean theorem, then you know, of course, that we easily can. So, a vital part of this kind of problem is to bust out the Pythagorean theorem, a squared plus b squared equals c squared, and figure out our c value, our hypotenuse. And so we plug in, and 3 squared is 9, yada, yada, yada. This shouldn't be new to you. And, what do we do from here? Well, we take the square root of both sides to kind of get c squared down to just c. And, I don't know, I can't help myself but point out that technically, like in a vacuum, if we were just solving this equation in a vacuum, we would get 2 answers. What would those 2 answers be? They'd be plus or minus 5, positive 5 or negative 5. But in context of the actual problem, we're finding the length of a hypotenuse, which of course cannot be negative 5. So, anyway, I had to say that. So c is 5. So that means that 3 over c just becomes 3 over 5. So final answer for sine would be opposite 3 over hypotenuse 5. Cosine would be, so ca, C-A-H would be adjacent over hypotenuse. Well, according to theta, the adjacent leg would be 4. We figured that the hypotenuse is 5, so, it's pretty downhill from here, isn't it? Like, once we know opposite, adjacent, and hypotenuse, OA and H, it's, like I said, it's all downhill. So tangent, so TOA would be O over A, which stands for opposite over adjacent. What was the opposite leg of theta? 3. What was the adjacent? 4, so 3/4. Excuse me. So here's a little callback to 1.2. Just like we did in 1.2, if you know the final answers for sine, cosine, and tangent, and you need the other three, we flip, flip, flip. So again, thinking back, hopefully you are learning this by heart now, even already. But which trig function, which answer do we flip to get the answer for cotangent? What's the reciprocal of cotangent? Tangent. So we flip that, 4/3. What's the reciprocal of secant? Which one do we flip to get secant? We flip cosine, 5/4. And of course, we flip sine to get cosecant. So we flip sine to get cosecant. And of course, pause the video if you didn't have enough time to write all that down. That's the advantage of these, having it on a video form. Next problem. Find the value of each of the all six trig functions of theta in the figure. Express each value in simplified form. Duh, always simplify. Let's see here. So according to the picture, we are given, what would we call 1? The hypotenuse, the adjacent leg, or the opposite. What's 1, as far as like the SOHCAHTOA ingredients? 1 would be the opposite. What are we going to call 5? What would be 5? 5 is the hypotenuse. So we know O, we know H, but we don't know the adjacent. So we're going to need to bust out the Pythagorean theorem again if we're going to, we need all these ingredients to figure out all 6. Only having the opposite and the hypotenuse, we can find sine and we can find cosecant, but not the other 4. So we need this. And, full disclosure, all cards on the table. The only reason, to really do another example like this is the whole Pythagorean theorem stuff. If you recall from junior high and whatever in geometry class, it's slightly different story, solving for one of the legs in the Pythagorean theorem versus solving for the unknown hypotenuse. Just as far as like solving for the missing variable, I guess. So I hope you know what I mean by that, but solving for the leg, you end up needing to subtract this over here, and then you take the square root of both sides and you get root 24. But as always, remember, you have to double check, or I don't know if double check, but you have to check to see if the square root of 24 can simplify, which it can. So this is how I do it. I break off the largest perfect square I can from 24, which is really just 4, and the square root of 4 I can do, and that's 2. Square root of 6 is still just the square root of 6. So other than the slightly different way we solve this Pythagorean theorem, because it's a leg, not hypotenuse, the rest is the same. O over H, A over H, O over A. And of course we flip the proper ones to get the other 3. And as always, for the millionth time, in some situations, I don't know, you would need to simplify this even more and rationalize this horrible denominator that has a square root in it, but not for me, and not on the AP test, which is what I sort of base my decision on. Anyway, moving on. Special right triangles, in other words, special angles. Really the only reason that we're going to talk about certain right triangles being special is because of the angles they have. So far, you can say that the only special angles we know of, and I mean really special, right? What do I mean by this? Like, if I said, find the sine of some angle, right? 50 degrees, 60 degrees, 70 degrees, 80 degrees, whatever. Are there any angles that you can do right now without probably using anything for help? No calculators, no looking up what the coordinates are online or whatever. Like, are there any coordinates that you would know, like, without any help? And I would argue that the really, really, really easy angles, again, are 0, 90, 180, and 270. And why? Again, because you could come up with those coordinates, I would hope, no offense, I would hope you would be able to, by now especially, I would hope you'd be able to figure out coordinates you can use for those 4 angles without any help whatsoever, without looking it up, without having a reference sheet, or whatever, or any calculators or whatever. This is bothering me a little bit. So, moving on. Just to kind of put this into action a little bit, the sine of 90, and just kind of for the moment going back to, the x, y, r definitions, because for 90 degrees we'd probably just go with the coordinates of 0, 1, where that's x, that's y, and therefore r would equal 1. And so don't forget, even though we're doing SOHCAHTOA now for a little while, don't forget that sine is y over r, and therefore it would equal, so that would be 1 over 1, which equals 1. And just another quick example to help us not forget about the x, y, and r stuff. 270, those are easy coordinates to figure out. Now watch me screw this up. But it should be 0, -1. And so that would make x 0 and y -1. And if we're using those coordinates, that makes r equal to 1. So never forget that that's y over x. And so -1 over 0. And definitely never forget that in mathematics, we can't divide by 0. It's not defined. And so this answer is undefined. The tangent 270 is undefined, or does not exist. Now let's get back on the main track, probably. Well, we can now include 3 more really, really special angles that we can work with. 30, 45, and 60. As long as you can remember the sides ratios for the special right triangles from geometry class. Okay? Now, what I usually say in class, yeah, I'll say this now. What I usually say in class is, if you were to memorize all of these crazy unit circle coordinates, okay, like I believe that for 30 degrees, don't write this down, but I believe 30 degrees, the unit circle coordinates are √3/2, 1/2, And the unit circle coordinates for 90 degrees, like we just said, are 0, 1, and stuff. So there's all kinds of angles. I know for the past 5 minutes I've talked about the only really special angles are 0, 180, 270, and now 30, 45, and 60. But last section, we did the sine. We could do the sine of 120 degrees, the tangent of 315 degrees. As long as we knew these crazy coordinates, right? But you kind of had to look them up. Like I had to give those to you, right? Now, Mr. Berchanowski, in his classes, their main strategy and what he sort of makes mandatory or necessary is to memorize all those coordinates, 225, 240, 60 degrees, 300 degrees, 330. 135. He has a really cool way, like it's fine. He has a way for you to memorize all those coordinates, and then you just use those coordinates. So this is one of the big differences, I guess, between the way I have you guys do problems and the way Mr. Burchanowski does. Excuse me. So, just to kind of reiterate that for a second, he has you memorize coordinates. I'm just going to have you memorize the ratios with like the 45, 45, 90 triangle and the 30, 60, 90 triangle. Okay? It's kind of a horse apiece. One's not better than the other. It's kind of the same. So do you remember how the sides kind of work? How can you describe the side lengths of a 45, 45, 90 triangle or a 30, 60, 90 triangle? And again, you probably had someone like Ms. Fetchko or Mrs. Clute, probably some other teacher other than me. And I don't know, maybe you started doing things like X and you worked with X, but what if I said that had a length of 1? If that was 1, then what would this length be? Wouldn't it also be 1? And how long would the hypotenuse be? Do you remember? It would be the square root of 2. Okay? Now, you might not have had, in Fetchko's class or whoever's class, you might not have written it exactly like this. It might have been like x, x, x root 2 or something else, but basically meant the same thing, whatever you did, if not this. And how about the 30, 60, do you remember how that kind of worked? Well, what if I said that was 1? What if I said the side across from the 30, in other words, the smallest side, because if that's 30 and that's 60 and that's 90, I don't care if you draw this triangle perfectly to scale or not. Whatever side is apparently across from the smallest angle is going to be the smallest side. So anyway, what if I said that was 1? How long would the other sides be? Would you remember? Would you know that the hypotenuse would then be 2, and the other leg would be root 3? Anyway, there it is. And in my class, on our very first test, you're going to need to have this memorized. So just saying, you got to remember that 45, 45, 90 is a 1, 1, root 2 kind of relationship. And the 30, 60, 90 would be like a 1, 2, square root of 3 relationship. Got to have that memorized. And then if you have that kind of stuff memorized, you can figure out the sine of 30, the cosine of 60, the tangent of 45, by using SOHCAHTOA. So see if you can fill out this chart on your own, like the sine of 30, or in other words, pi over 6 would go here, the tangent of 60 would go here, the cosine of 45 would go here. See if you can fill out this chart on your own, pausing the video, okay? But, so the sine of 30 would be opposite over hypotenuse, for example. So that would be 1/2. The sine of 45 would be opposite over hypotenuse in that other triangle, which I know I don't make you rationalize denominators like I've said 100 times, but I'm still going to say this and mean it. You should definitely remember and realize and understand that root 2 over 2 is equivalent to 1 over root 2. So please make it a point to write this down in that spot. The sine of 60, doing the opposite over hypotenuse there, root 3 over 2. And that would be that. And going through all of the, see now this would be adjacent over hypotenuse. That would be that. Tangent of 30 Tangent of 30 opposite over adjacent. TOA. If I'm not mistaken, that's going to be 1 over root 3, which, again, you should realize that root 3 over 3 is the same thing. Tangent of 45 is going to be 1 over 1, so 1. And this should be root 3 over 1, which is just root 3. Moving on. So far with these right triangles, whenever we had to evaluate a trig function of some angle, we've always known what the sides were, or at least we could easily figure out what they were. We always knew what the hypotenuse was, the opposite side was, or whatever, so we could plug them into the proper ratio, you know. The blank wasn't always necessary to know. The what? The angle. Who cares what the angle was as long as we knew, you know, we could find the sine of an angle. We didn't need to know what the angle was as long as we knew the opposite leg, how long that was, and how long the hypotenuse was. We didn't really always need to know the angle. So, kind of a new kind of problem. How could we find out what the missing side is in the following situation? So we know that this angle is 24 degrees. The adjacent leg is 750. We don't know the opposite leg, and we don't know the hypotenuse. So here's the thing. Hopefully you realize this pretty quick. We cannot use the Pythagorean theorem to figure out A, right? So what do? Here's what we do. We use a trig function. Which trig function are we going to use? Sine, cosine, or tangent? Which one fits this particular situation? You know, where we have the adjacent leg and we want to figure out the opposite leg. Wouldn't it make sense to use tangent? Because tangent involves opposite and adjacent. So theta would be 24 degrees. We do not know the opposite leg, and the adjacent leg 750. So what do we do now? We just solve for A. If you want to think of this as a proportion, like if you want to think of this as, you know, tangent of 24 degrees over 1 and then cross multiply, whatever. But all we really need to do to get A by itself is multiply both sides by 750. And we're actually going to use a calculator to do this. It's the only way we're going to be able to do tangent of 24. So 750 times the tangent of 24 degrees. Make sure your calculator is in degree mode. You're not doing 24 radians, you're doing 24 degrees. And that should be, let's see, approximately equal to 333.922 yards. So we're going to approximate to 3 places. Okay? So that's the answer. Moving on to this problem. What if it was the angle that you needed to find? So in other words, what's theta? Okay? Looks like they gave us the opposite leg and the adjacent leg, which, that's going to imply tangent again. So here's what we do. Tangent of theta equals opposite over adjacent. We do not know theta this time, but we do know that the opposite is 21 and the adjacent is 25. Okay? I know that doesn't look a lot like an 8, but I'll make sure that looks more like a 5 and not at all like an 8. Okay. What do? It's the angle we want to find. Okay? Like, we know the final answer, 21/25, but we don't know the angle. What do we do? What do we do? What do we do? Well, we actually do the inverse tangent. All right? The inverse tangent pretty much means you swap input and output. You'll probably at least once have to hear my whole spiel about how, you know, this whole -1 notation is kind of misleading, but you're going to be doing this on a calculator. So this is how it's going to look on your calculator. You're going to access the inverse tangent, you know, on your calculator. Because now it's like the output becomes the input, and the input is what we're trying to figure out as output, you know. But again, the bottom line is you got to remember that when it's the angle you do not know, but you do have the final answer, you're going to use the inverse tangent function in your calculator. Okay? So, using our calculator, we have to hit the second button, you know, like the shift button. So we do second tangent, which accesses the inverse tangent. And now I'm just going to do 21 divided by 25 right here on the calculator in parentheses. And calculator says that theta is about 40.030 degrees. All right? Make sure that even as you're just kind of copying this down, please grab a calculator. I hope you have one nearby handy. Make sure that you know how to go through the motions and press the buttons and whatever. You should do this on your own and make sure you're able to make your screen say 40.030.25927, whatever. All right? I guess that's it. Oh, wait. No, it's not. Hold on. I wanted to point something out real quick. Back to here. Just in case I don't get a chance in class or whatever, or if we haven't already, I want to make you aware of a slightly different example of this, okay? When we plugged in everything to opposite and adjacent, we ended up with A over 750, you know? And solving for A was as easy as just multiplying 750 to the other side. I just want to point out something really quick. I'm not going to actually carry it out all the way, but if the variable would have happened to been in the denominator, like let's say this would have been 750 over A, okay? Solving for A would have been at least a little bit more complicated than it was here, where all we needed to do was multiply both sides by 750. If A was on the bottom, you know, it would have been at least slightly different. So you got to be on your toes about that kind of stuff. It's just kind of like a solving for the variable kind of thing. And now I'm done.